Welcome to my presentation. My name is Figueredo. I'm going to talk today about robot contact reflex and adaptive maneuvers the robot can take in case of collision. To start, we perform evaluation of different reflex maneuvers. We use the PUSE robot measurement system to measure contact forces and to compare 9 reflex maneuvers under 7 different criteria. We evaluated the mean standard deviation of all the experiments for all performance criteria, which include maximum contact forces, mean statical forces, exchanged energy, the contact duration, of course, less contacts, less time of contact, the better, change in momentum, which induce lower chance in secondary collisions according to collided entity. A maximum distance travel, lower distance reduce the risk of secondary collisions of the robot, of course. Here you can see the experiments that we performed using the measurement device. We performed in total for each system, for each reflex, we performed 12 different types of experiments with 4 different velocities, 0.04, 0.08, 0.15, 0.25 meters per second, with 3 different materials emulating different parts of the human body. A hard one emulating the forehead, a medium one emulating the calf muscle, and a soft one emulating the abdominal muscle. We performed 10 trials per combination, which means that we performed more than 1,000 trials in total. The reflex maneuvers we experimented were divided between 3 categories: stop maneuvers, active retraction maneuvers, and retraction through back abilities. So going first to stop maneuvers, this is basically the stop reflex that is basically fix the current position once the contact is detected. Active retraction maneuvers that retract in the direction of contact forces and include Cartesian retraction based on Cartesian impedance controllers, joint retraction, which is naturally based on joint impedance controllers, and stop retraction, which is based on the joint retraction after stopping for 200 milliseconds. And retraction through back variability, which roughly emulates a passive damping reaction and includes admittance with and without stopping at the distance of 2 centimeters, 0G, pure visco damping, super 0G, 0G with inertia shaping, making the robot lighter, and super stop, super 0G, and stopping after 2 centimeters. So these are the same results now in slow motion. So you can see the response of each reflex maneuver. You can see back to real time. So there is quite a lot of information collected from these experiments, and we are making it available for everyone to see and to use. I'll include the link in the end of the presentation for all the data, but this is also included in the paper. In any case, the main takeaway message here is impact is uncontrollable. The maximum contact force is roughly the same for all reflexes and vary mostly with the velocities and materials used, and of course reflect the mass. But now when comparing reflex maneuvers, the main takeaway message here is, and overall, all reflex behaves roughly the same at the impact phase. Thus, the choice of reflex should focus mostly on the trade-offs of the post-impact phase. For instance, in terms of distance traveled, energy exchanged, and object conformability and task requirements. With the information collected from the experiments, we tried to answer in this paper the question of how to incorporate reflex into a robot control system. Naturally, you assume a complete real-world scenario where we can have some global task planning entity and a state observer, as well as a motion generator that translates the goal from the task planner into trajectories for the robot controller. Now, instead of feeding the result trajectories directly into the controller as usually done, we introduce this additional layer that we namely Reflex engine running together with the controller inside the real-time control loop. The Reflex engine can alter the trajectory in the case of unforeseen collisions, for instance, that would be observed by a real-time contact observer. And it is further able to change the current controller and its parameters, and is connected to task planner to request replanning in unrecoverable situations, and the motion generator is therefore able to change the velocity of the trajectory and request the generation of recovered trajectories after the reflex. The reflex engine itself is implemented as a state machine that can use decision trees based on the globally observed state. The reflex engine that we propose, that is quite general, has different states. In normal operation, the trajectory from the motion generator is simply forwarded to the controller. On a light contact or change in the global state, in example, if a human enters a workspace, a reaction in the interaction is performed. This reaction does not stop the trajectory, includes, for instance, a change in the time scaling of the trajectory, adopting the trajectory according to an additive control law. On the stronger context, however, a reflex similar to the ones investigating the previous experiments performed that would temporarily stop the execution. After the reflex ended, the robot waits for some input of the user to recover from the task. In the recovery state, the robot signals the motion generated to generate the recovery trajectory, bringing the robot back to the position of collision and continue the task from there. In case something going wrong during the reflex, for instance, an active retraction is causing a secondary collision, the reflex engine enters a fallback state, where the robot will execute a fail-safe behavior, for instance, stopping reflex. Finally, we demonstrate the approach with an example task where the robot has to pick up the black container and dispose its contents into the blue container. Top left graph shows a simplified version of the state machine where the active state is marked in green. Top right shows the scene from above. Bottom left is a live plot with the robot position, absolute velocity, tilt angle around the z-axis, external forces, and external momentum. Now, when the robot enters the scene, the desired velocity reduces. A push opposing the direction of motion is reducing the desired velocity further. Interaction push orthogonal to the direction of motion activates an unit sense constraint reaction, and after that, a zero-G reflex is triggered that allows free motion, including change of orientation of the effector. Recover mode brings the robot back to the collision point, and several push in the direction of motion during recovery lead to increased robot velocity. When the robot is finally holding the container, the reflex is constrained to the orientational aspects, such that the contact does not cause the content to drop, as you can see. The overall takeaway is that despite heavy disturbance and several interactions, and reflect that the task can be accomplished successfully. Thanks for listening. The experimental data can be found under the link and with the QR code on the side.